Okay, so hello everyone. Today I'll be talking about human deep learning for humans. So let's start. So each slide is a promise. It's a promise to deliver some kind of concept to you. This slide promises you to deliver the type of human deep learning for humans. So let's put it into pieces and try to understand what I need to deliver in order to make you happy. So the first thing is actually understanding the concept of deep. So we will talk about how actually the deepness or actually the number of layers in the neural networks, because today I'll be covering most of neural networks, are actually influencing the results that we are getting from such systems. But before that, we will dive into the abstract notion of learning and, most importantly, of learnable. So something that is it's actually always neglected in all of the machine learning courses. And unfortunately, during such conferences and scientific conferences, people are always outlining the toolboxes, outlining the tools, and saying there is this new amazing library that you should use. And the biggest problem of that is that at some point developers are saying like, yeah, you know, this library is a bit too confusing, it's too complex. And there is a very simple explanation behind that, is because you don't understand the library. Because it's super complex, and when it comes to artificial intelligence and mathematics that is hidden underneath is incredibly sophisticated. So the goal of this talk is to teach you the concepts that will help you next time you will go through the documentation of Piano or scikit-learn or any other framework that you love. Or if you would read some next amazing article from Google saying that this time we were able to beat human in this and this task, you will know what they actually used, what is the technology, and what is the background, so that you will think that you are in control. So let's get started. So what is learning? The learning is a process that could be described, unfortunately, from the perspective of our educational system in this way. I'm not sure whether you can see it. I was quite surprised by the size of the projector, so sorry for that. So there is a data, there is a learning process, and there is a goal that we need to achieve. And this is what our teachers in schools are telling us. So one of the examples of that is you have the whole bunch of French words. Let's say that you are studying French. Your learning process is super inefficient remembering of the words, but of course you will apply this process because you know that in the short time you will be able most likely to achieve your goal, which is getting high score on vocabulary tests. And I think we all know this process. And from the human brain perspective and neural networks and the complex systems, is most likely the worst approach you can have in your life. But let's try to get into one more example, something that may be much closer to you right now. I know that TDD is a very fashionable phrase. Unfortunately, lots of developers I'm talking to, they know a lot about TDD, but actually their knowledge ends up on the theory. And then they're always saying, but by the way, we tried that, but there is management. And management said, we have some deadlines, so maybe you can try TDD in your private project, but here we are producing code, right? But TDD is just a beautiful example of much more organically correct, much more efficient process of learning. Basically, you start with the technical specs, with a list of them, or some natural language description of the technical specs. Your process is TDD, and your goal is pass the specs. But the thing is that this example is not really aligned with the diagram I showed you before, the educational one. It's more like that. So you start with your spec, and most likely you will take the first of them, or you will generalize the spec and you will say, all right, so I'm supposed to build a function, and the function should return. All right, so that will be your first test. I'm going to test that such a function exists and it returns. All right, so that was your input. Your goal is the shape of this super simple function that just returns something, some given type. And then you are getting back to your data, to your spec, and say, all right, now I established this goal. Let's climb higher into my ladder of specs. And in other words, you'll be cycling this way, and probably you already know about TDD, that this is how TDD more or less is defined as a cycle. But if you ask yourself, all right, so with TDD as a learning process, we are getting closer to being more human, or being actually much more efficient when it comes to taking into account the kind of hardware we have. but how should it look like? What's the reality? And the reality is like, of course, this is quite simplified picture, but the reality is that we are always going from one state to another state. There is no distinction between the goal and the data. And this is something for lots of people hard to imagine, because we tend to think in this dualistic way, that there are the data, there is an input, and there is a result. And unfortunately, educational system, and then universities, and then the job is keep ensuring us that this is the way to go. So you will be a good developer, you will get a good salary, you will be a bad developer, you will get a bad salary, and this behavioristic kind of approach is making us stupider, in my opinion, and much more shallow. So this is an example of the state that should be that is a realization of how it looks, in my opinion, in reality. So we go from one activity state of our neurons to another one. So in other words, something that you should have in mind is that neural networks are not the systems where you have some black box and you put some lots of data on them and they magically will create a solution. The neural networks, with their weight, is a compression of data. The neural networks, trained neural networks, is a representation of the data. And I will give you an example of that. If you would close your eyes right now, you don't have to do it. And I will tell you, all right, so instead of running in the input mode, just by listening to me and just processing what I'm saying, how about you work in the generative mode? In other words, you can close your eyes and I will say, let's imagine that you are on the seaside and you are walking, everything is relaxing. Right now you are generating the world. So, in other words, you are the data, right? And the neural networks are the data. So, but most important term that is always neglected is the learnable. And it's so much neglected that dictionaries do not even have that word. So my dictionary is always highlighting it like, hey, it doesn't exist. Did you mean learning? No, I meant learning. All right, so let's hear Mr. Mark Twain saying all generalizations are false, including this one, which is quite nice statement. But what is most important here is that when it comes to machine learning system, artificial intelligence in general, you need to take into account that what is very, very crucial for us is the generalization. And this is for us as a human being something that is totally crucial, because without generalization we will not be able to train ourselves in one kind of environment and then go to another environment and survive them. So essentially here, learnable is about generalization. And throughout the talk I'll be showing you some of the nice things, because I noticed that lots of people like to do these snapshots photos, so I thought like, that's the best way to reference. So basically this is an amazing book about the theory that I will just outline to you in right now. So let's ask ourselves, what is the relationship between the environment and relationship between the environment and generalization? So the acquired skills should be useful also in the situation not encountered during the learning phase. This says that you train yourself in one environment, and as I said, your data is your neural network. You are the data. In other words, you are the environment. All right? The model of human brain being a processing machine where we have some input from the outside and then some magical things is happening and then you have the understanding of the world is totally wrong. And we know that for a long, long time, but unfortunately lots of books in biology are still not updated. But in other words, here the statement says that you live in some environment, and the environment in terms of algorithms are the data, are the sample data that you are feeding algorithm with. And of course what you want to establish there is like you would like to get into generalization that is good enough for other data that was not seen by the algorithm. So something that is, some people could say like, yeah, this question is totally stupid. When generalization can occur? It can occur always, some people would say, because of course it will be better or worse, but some generalization will always happen, all right? Even if you overfeed your data a lot, there will be some generalization, okay? So maybe in some logical way this question is stupid, but actually it's not, because as it occurs, our world around us fulfills two conditions that makes us privileged enough that our algorithms are learnable. So one of the assumptions is invariance assumption. Invariance assumptions is actually the statement we just encountered, saying that the type of environment or probability distributions of the world or the events that are occurring around us should be similar in the environment where you train your algorithm and the environment where you test your algorithm. So one of the examples of that is if you imagine that you have two kinds of fruits, one is eatable and second is not eatable, and you would like to train yourself to distinguish between them, all right? And now imagine that it happens on some beautiful exotic planet somewhere in the universe where those fruits keep changing their features, where they are not stable, where they are changing colors all the time, where they are changing shapes all the time. In other words, that prevents you from really finding some invariant features that will allow you to distinguish between them. The second one, which is much more important, and is a fundamental law of maybe even the universe, is learnable regularity assumption. So in other words, you need to probe the world, but your time is finite. Something really sad. I hope that you make it sad too much, but we'll all die one day. And we have finite amount of time to probe the world and to train our classifiers of the concepts in an efficient way so that we can survive till 120 years old. So learnable regularity assumption says that the features that will allow us to distinguish between different concepts needs to be detectable, obviously. And detection algorithm is feasible. What does it mean? That all the numbers, all the things, the number of interaction, time we need to spend is polynomially bounded. In other words, we cannot spend forever on just trying to classify one thing. And maybe those statements can sound to you a bit trivial, but let's see some examples. So we go to marble world. We have a marble world, we have the cylinder with a lot of marbles inside, and enumerated with numbers 1, 2, 3, 4, 5. And here is an example of the world where each one of them comes in the same quantity. And our algorithm, something that we need to train, is an algorithm that will tell us what's the representation of that world, how does it look like, all right? And this is how you probe the world around you. So basically we can do 100 picks. And after those 100 picks, we want to say, all right, so in my opinion, 30% of the space is taken by 5s, and 10% of the space is taken by 4s. And of course, this would be some reflection of that world. This is the very idea of this random sampling. But the problem is that of course, sometimes the world that you are dealing with, or the number of times you are dealing with, is quite incredibly big. So, just to give you one example. So, for example, you can say, all right, so our experiment is totally random. But we could already calculate, for example, what is the probability of never getting 1. And never getting 1. So, for example, we can say, is it possible that I will, by probing this world, I will learn it in a way that I will never encounter 1. In other words, my representation of that world would be a world where we have only 2s, 3s, 4s, and 5s, and never 1s. And of course, the probability that you will never get 1 is super small. Of course, we need to remember that sometimes we are dealing with quite exotic worlds. And one of the examples of that is that when you have just single specimens of a given type. And now if you ask yourself, and let's get back to Mark Twain's words, is what about those generalizations? If I would pick 100 marbles from here, and 100 of them would be blue, would be 1s, is it bad or is it good? We will generalize based on that. We'll say every single marble inside the cylinder world is blue, is 1, all right? And someone will say, not really, there are some rare cases, okay? But of course that person would have to do his picks as well. But the thing is that from the statistical perspective, since there is such a huge prevalence of the 1s, we will say, yeah, that's totally fine. That's your representation of that world, that's your statistical approximately correct representation of that world, and it's good enough. And so, for example, we can write some precise calculations in this example, where you can imagine that those guys are taking 5% of the space. And then we will say that with 97% confidence, we know that after 100 picks, one can see representative of 80% of the contents of the urn. And that's fixed. This statement is fixed no matter how you will do your experiment. In other words, this is something magical here, the magic of mathematics, telling you that no matter how crazy your process would be, if you mix after each peak, if you just, I don't know, keep the cylinder or whatever, you will always end up with this statement. So in other words, this is how we are able to probe the world and how our algorithms of deep learning systems are able to probe the data. But let's get into much more realistic example, because this is something that always gets me appreciate the beauty of the algorithm of deep representations and mathematics, because the world we live in is full of those variables. The 5 types is totally not realistic. Imagine the situation, you want to distinguish between animal and plant, and you want to train a classifier that will do that, and you have 20 features, and they're all Boolean, has ears, has leaves, has blue, etc. And by just taking this number and taking into account the fact that it's Boolean, we end up with more than 1 million possible species. And naturally, it's exponentially many. And we know that the elements around us are incredibly complex, incredibly complicated. And of course, the 20 features is a bit too little. So in other words, something you need to really understand right now is the world around you is exponentially complex. But exponential is a very bad word, because this word tells us that essentially we will have to spend incredible amount of time probing it. Probably we will die until we will actually classify, to train our classifiers to distinguish between animals and plants. And we know that in our survival run, it was quite important to distinguish. So we get to the concept of the learnable, and the learnable is that learnable algorithms should learn from a number of examples that is polynomial number of features, and one can control the error and insist that this control be, again, polynomial. In other words, what is super crucial for us is that we need to find our way in the exponentially complex world using only polynomially bounded resources, because otherwise we'll die. Alright? And what is really incredible, and this is a statement that you need to keep in mind when in like 2-3 minutes we'll get to the deep learning systems, is that only certain very limited, and by very limited it should be like very limited classes of functions, can fulfill the above condition. In other words, we are not privileged enough to throw whatever function we want on our data and say like, yeah, probably it will be able to classify something. It appears that it's a very limited amount of functions, and it's still a question what kind of algorithm is used by our brains. But what is really important is that 2 functions that belong to that is the linear separator and conjunctions. The conjunctions is just a statement where you have lots of booleans that are glued together with AND. So basically, AND operator. So you can have has ears, and has fur, and has something, and it is blue, and this is actually an example of some nice animal. And so PAC, which is probably approximately correct, which is a theory of learnability, states that learning process takes limited number of steps. You see 2, otherwise you die. The computation requires only limited number of interactions with the world. Yeah, it's the same. Learning leads to categorization with small error, and this you need to have. And those are very strict conditions. So again, please realize the importance of this statement. You are in the exponential world, where the number of species grows like crazy, and you have limited amount of resources, and you need to do small error rate. That's very important. Small error rate, because otherwise you don't want to eat uneatable fruit. Alright, and so what's the role of the teacher? Because all the algorithms, we are getting into showing you a bit more algorithms, otherwise you'll be super bored. So what's the role of a teacher? The teacher serves you the right examples at the right time. At least this is what they're supposed to do. So in other words, they should comprehend what's your current understanding of a given concept, and then start to build on top of that. And this is the most successful teachers. And of course, when training, for example, deep learning systems, you can play the role of a teacher as well. It's really important what is the order of serving your samples, of actually serving your data. And something that is incredibly beautiful is the very notion that the evolution is a learning process on its own. So the thing around you is just like a weight in the neural network. So this room, you, how we look like, and all the stuff around us is just a result of the current state of an evolutionary process. And it's really important because then you can ask the question, so why the world around us is learnable? Because it's evolved. So the thing is that sometimes because of the Descartes error, like philosophical error, and the notion that there is a brain, and so there is a mind, there is a body, and all around us, so this division into three entities actually harmed us a bit, because we do not realize right now that the world around us is basically us, and us is the world around us from the algorithmic perspective, even though it can sound quite philosophical. And so then I started to pursue this idea and thought, alright, so can you breed the intelligent systems? And this is called neural evolution. So basically, instead of back-propagating or training your neural networks in the classical way, you can just create thousands of the neural networks randomly and make them do some tasks. They can compete, and this is quite often used when training gaming algorithms. And then you just select the one that survives as the best player. So this is the idea I learned from the Blondie 24 by David Fogel, who is one of the major researchers in the field of evolutionary compilation. And he created this bot, Blondie 24. And his idea was to create a bot that will play checkers. But the thing is that there were no data he provided for Blondie 24. Basically, he was just creating thousands of neural networks, and they were competing. So they were predicting the next move, and then they were competing against each other, and then he was just running it for weeks and weeks and weeks. And then as soon as he got some instance that was good enough, he was actually using it to play against humans. So Blondie 24 ended up as an expert in checkers. It won a few tournaments. And the thing is that I wanted to show you this because I'm a big fan of the real artificial intelligence. I know that the industry needs to use artificial intelligence to boost their productivity and sell more stuff. But the real pursuit of artificial intelligence, in my humble opinion, is to really understand how the human brain works. And this is a beautiful example of actually this kind of pursuit. For example, the Deep Blue that was facing Kasparov is not an artificial intelligence. It's just one huge computer that has a whole bunch of heuristics and manually tuned weights. So this is not a system that learned how to play chess. It was taught how to play chess, but in the worst case possible. So you can imagine that your teacher is opening your skull and just tuning some of your weights, and then just go play with Kasparov. Alright, but when I got really into this idea, and I thought, alright, so I would like to tell the guys during the conference about this, so I thought, alright, I will take one of the classical examples, and it's traveling salesman. So this is the example. So you have 50 cities, and there is a guy who needs to sell things, because he works in the commercial artificial intelligence, so he needs to sell a lot of products. And he jumps from one city to the other, and of course he needs to optimize. So he wants to reach all the cities only once, return to the starting position, and of course he wants to minimize his route. So this is the video showing you how the algorithm was calculating the whole evolutionary process, the process of finding the optimal path. And what is really important here is that sometimes you can see that this thing is moving and this like stops, freezes. Because at some point for quite a long time, we have a specimen that is strongest, and it's really hard to compete with this guy. And what is really, really crucial here is that if you calculate if you would like to tackle this problem in the brute force way, you have 50 factorial possibilities. So of course, no way you can calculate that. But if you will do the evolutionary one, and this is the end result, it's good enough, as I said. It's good enough. We don't want to find the best. This is good enough. And why we are happy with this is basically this guy was, he only searched around 400,000 states. So 400,000 compared to 50 factorial, you can nicely approximate to 0. So in other words, from the incredibly factorial space of all the possibilities. So imagine that you have this super 50-dimensional space where you have all possible solutions. This guy had to only reach only incredibly neglectable fraction of them to come up with this solution. And this is what is called intelligence. This is another example. So I was like, I need to admit that I'm not smart enough to solve the Rubik cube. So I was like, oh my god, like everyone is solving the Rubik cube, and always my friends who are not from the world of science are always asking me, alright, so can you solve the Rubik cube? And they're always asking me a question, in how many seconds? I said, man, like you can give me 24 hours and nothing will happen. You know, but the thing is that then I thought, alright, I want to use artificial intelligence to make me better. I cannot afford a teacher to teach me how to solve Rubik cube. But I thought, hey, maybe I will build an artificial intelligence system that will teach me how to do Rubik cube. I'll be just watching the artificial intelligence actually trying to solve it. So I just used the David Fogel idea, and it's very like rough implementation. And what I really wanted to see, whether this guy would be even capable. Oh, here we go. So basically, and that's artificial intelligence solving it. So basically, I'm just observing this guy just in slow motion, actually trying to figure out what kind of strategies this evolved intelligence is using. And you would be actually quite surprised to see that some of the patterns that this guy came up with are quite like original, like so non-human, I would say, that they're like quite crazy sometimes. Sometimes you take some root and you think like, oh god damn it, it's just scrambling the cube even more, because I can see the score of scramble on the left. And then I realized, wow, something beautiful is happening, and the guy just finished. So I couldn't predict that. So my intelligence is not as good as this one. Alright, so let's get to the concept of deep. Because everyone is talking about deep learning systems, about deep neural networks. What is so important about the concept of deep? And before we will get that, you need to understand one concept, backpropagation. So backpropagation is a way to teach. So one of the ways of training your neural networks is through evolution. They can compete. Alright, so you can search this space of all possible solutions by just evolving them and making them compete with each other, which is really beautiful, because the thing is that this is kind of unsupervised way of training them, so you don't need to have a whole bunch of examples. You just run your computer. If you have one spare laptop, you just put it on like 3 weeks, and then you go back and see how it works, or oh, it doesn't. All right, so in order for you to understand about propagation, and if you will be reading any documentation about the deep learning systems or the packages, or if you will be reading algorithms or the articles about deep learning systems, it's quite important to understand the concept of backpropagation. And to help you understand this concept, let's focus on so-called computational graphs. So here you have some algebraic statement where you have two variables, dependent variables A and B, and then you have the third one, the output, which is E. And let's call our actors. We have the input A, B, and we have output E. That's it. And this is how neural network works. You have input and you have output, but let's add some hidden layers. So the hidden layer is like sometimes you say, all right, I can factor out some of the expressions, and I will say, all right, I have my inputs again, A and B, but then I have intermediate variables, C and D, and then my output. And this is the world of the neural networks of deep system. Oh, this is not deep, it's one layer, but it already has hidden layer. So the backpropagation is the idea of you train your network, you put some output, and you have some input. You put your input, and you have some expectations towards desired output. And then you compare. You just give your input, your neural network says, that's an apple. And then you see that actually it should be a pear. So you say, there is some error. I need to backpropagate it to correct the weights. Alright? And the way of propagating it, and sorry for that if anyone had nightmares about mathematics in university. For that you need to use derivatives, and derivatives are a notion of a change. So I want to backpropagate a change, alright? So what I want to backpropagate is actually the change of what is the influence of this particular input of A on my output, alright? And this is it, that's so simple. So backpropagation is just a notion of chain rule and sum rule, and that's it. So, and I think that's really important. If you ever go into the field of deep learning and neural networks and you start reading articles about backpropagation, unfortunately, 99.9% of the time, you will start to see these equations with like 5 indices and like a few sigmas, like sum symbols, and you say, oh my god. But at the end of the day, backpropagation is just a chain rule. So in other words, if I want to understand what's the input, what's the actually influence of the input A on my output, I just need to ask yet another question. All right, so let me rephrase it. What's the input? What's the influence of the C on E? So in other words, I just backpropagate. I calculate it back, which is just a chain rule from the calculus. Alright, and something that is the most beautiful results of the deep learning system, and this is where all the things that we cover today will start to fall into one place. So imagine the following situation. This is our real neural network. We have 2 inputs, 2 outputs, and 2 hidden layers. And this is adapted, by the way, from Andres Carpet's demo, which is really, really beautiful. And we have this kind of triangular kind of data. So we have 2 types of objects. Red types and green types. And what do we want to do? We want to train neural network that will be able to separate them, to really distinguish between those 2 concepts. Because in this form, it's not learnable. Because you remember what is learnable? Linear separator. I can't draw a line to really separate them right now. So this is impossible to solve. You cannot think about linear separator that will be able to do that. And we know that in our universe, at least, the linear separators are the one that were proven to be learnable. So, let's try to, I don't know whether you can see it at the back. Well, can you see that those 2 neurons are activated? And a volunteer from the back? Okay. So, in other words, here's the input, and we are looking at those 2 neurons, at the activation, and we just paint it. We basically just map this to that. And this is just before we apply the activation functions, alright? So what we can see here is that till that point, when you reach that point, we just did the matrix multiplication. Basically, we just skewed it a bit and rotated a bit, and as you can see, yeah, this is what happened, nothing particular. It's not separable, but as soon as we'll apply the activation function, this is the same 2 neurons, but we just applied the hyperbolic tangent, we see that something started to happen. It's still not separable, but something magical starts to happen. In other words, you can see that this guy, the thing that was just embedded inside the red zone, starts to move outside. Something nice is going on here. Alright, and this is another 2 neurons, their activation. They take the inputs from all the neurons from the hidden layer. And what you can see here, and this is again before applying activation function, you see that something magical is happening. It's like this topological transformation happened, which pulled those elements away from the red zone. And then after applying activation function, and the final, and that's magic. Because here I can just say, that's a separation. Alright, so I can train the linear separator and the universe is happy because the PAC happened, and that's why deep learning systems are so successful. They can take things that are not separable and separate them. What is also important for you, I promise in the description of the talk that I'll be talking about debugging and the tools to read optimized neural network. And this is an example of that. Just looking at the activation images of your neurons. Basically, while training it, you can have some nice, I don't know, you can build a nice Django interface just to observe what is happening. And you're successful if you are getting close to being successful at training your neural network. You should start to see that some separation is happening. If you ended up with some mixture even after the 3rd layer, something is totally wrong. Your architecture is wrong, or your activation function, lots of choices. All right. So the question is, like, some people ask, all right, so can the representations be useful on their own? And this is incredibly important question personally for me, because I think that the artificial intelligence should be created to enrich us, to actually help us see more than we can see right now. Because if there are some things around us that unfortunately this algorithm is not able to separate, to actually conceptualize, we will never perceive it. So the bold statement is like, so maybe we will be able to train artificial intelligence that will transform unthinkable into something that will be thinkable for us. And now the question is about the representation. So the example of representation you've seen in a few seconds ago, by just showing you the state of the hidden neurons. But some people took it very seriously. This is it. Again, Andre Carpenter is showing. He just mapped 50,000 images into multidimensional vectors, and this mapping happened through the neural networks. And what happened is that when he plotted it, when he reduced the dimension to 2, and he plotted it, he started to notice, oh, things that are alike are close together. And that's beautiful, because you just put it together, you just mapped the images using convolutional neural networks to some new representation, and you ended up with a new space where images are not pixels, where images are concepts. And those concepts, you see, there is a bird, or there is a football and a bird, but this looks like a football, maybe. Alright, well, you got my point. So, another very successful example of the very same concept is word embeddings. So word embeddings is transformation of words into multidimensional vectors that are living in the space of concepts. So in other words, again, they are not a character, ASCII characters or whatever. They are concepts. And if you plot them, if you plot this multidimensional space and you just dump it into 2 dimensions, you see that the things that are alike are going together. And this space is really amazing, because this deep learning system, what it achieved is that the concepts are not only the positions of those elements and the distance between them, but also the directions and the differences between the concepts. So for example, you can show that the distance between a queen and a woman as a word, and a king and a man is the same. Basically, it's grouped together not only the single words, which are alike, but also you can do some crazy stuff inside this space. And of course, right now it's a super hot topic in the world of natural language processing, and lots of people are talking about that. And what is really funny always, like when I'm attending such talks, people are saying, like, who are presenting that, are saying, like, so everyone is talking about the word embeddings, and at some point you think that the world is composed of people working only in the artificial intelligence field, and that everyone is talking about it, and then you realize that no one is. Alright, so but let's ask ourselves a question again from the human perspective. So, alright, so we showed even some examples of the neural networks. We showed how we can perceive different representations of it, how the neural networks can actually teach me how to solve the Rubik's Cube, how it can beat masters in the checkers. But what about human perspective? And one of the most successful neural networks architectures right now, something that is beating everything, especially for image processing and image classification, are so-called convolutional neural networks. And convolutional neural networks are applying the idea that already lives in our neural cortex. So basically in our visual cortex, we have multiple layers. And each layer, each neuron, because the examples I showed you before, they were fully connected. Here we are looking at the patches. So in other words, each layer by layer, is looking at yet another patch. So at only the subset of the space. So in other words, this way you can train your lowest layer to recognize edges and angles, for example. Then another layer to recognize some L shapes, T shapes, and so on. And then another that's recognizing already some small concept, I don't know, finger, whatever. And then yet another, which is a human. And some people are saying that in the real brain it works in a way that the highest level, the highest invariant level, the highest concept is just you. And this is actually the consciousness. So, but I don't know. This is too sophisticated for me. Alright, but I wanted to show you, the last thing is that I wanted to show you how you can use this concept to maybe start to look at the way you learn and you acquire knowledge. And for that use case, I picked up the foreign language acquisition. So I thought, alright, so everyone is smart about education, so I thought if I ask myself, but take into account the knowledge from deep learning systems, how would I study foreign languages? And first thing is that, of course, it needs to be curricular driven. So, and the problem with the schools is that we start from words, and they give us a whole bunch of lists, and we end up with the first slide, one of the first slides with the data goal approach. And what should be really a case is that, first of all, please realize that unfortunately in the schools, learning of languages always starts from the written language, and the real test of your language is such a conference, for example, where you speak with the people. And those two modalities are not really working nice together. So basically, the first thing you should really acquire is the recognition of the specific phonemes of a given language and chunking. And then the words recognition comes. Without chunking, which is a way of splitting a foreign stream of sounds into meaningful concepts. Alright? And then of course the sentences are coming and so on and so forth. And the other one is naturally unfolding examples, something that you always need to have in mind. Unfortunately, most of the time we are being given a list of vocabulary to learn, or the tasks to do, and what we should actually do, we should use our brain in the generative way. So instead of waiting for someone to give us examples, you should ask yourself, alright, so I know the words for blue and yellow, what should be the next that I really need? And maybe it's red, okay? So, of course, you can ask those questions in your mother tongue and then drive your acquisition of language this way. And something that is really, really important, and something that, in my opinion, internet is violating a lot, and is the laziness principle. So, but reverted. So we have lots of portals magically telling you that you'll be able to acquire your language in 1 week, 2 weeks. If you put some probes on your skull, it will even 2 hours, whatever. But the thing is that motor cortex, the part of the brain that's activated when you create something, when you write, when you draw, is super essential. And for example, the flashcards is a beautiful example of that. If you really want to use flashcards successfully, make them yourself. Buying flashcards is totally inefficient and was proven many, many times. Of course, the flashcards works for the short-term memory. That's why people perceive them as super successful, because just before the examination, they just go through the flashcards and they're like, yeah, I know it. 1 week later, what was the examination about? I don't know. And the last point is that it should be interest-driven. So, in other words, you should remember that your brain, your mechanism in the brain, your neural nervous system is aware about the complexity of the world around you. That's why it probes it selectively. Your brain knows about the polynomial limit. In other words, if you really want to acquire something, you need to start to focus on those things. You need to allow yourself to, first of all, unfold the examples naturally, and then activate the examples by creating the macros, the learning macros for yourself. And before I will conclude, I would like to thank Christopher Olam for creating his amazing blog about the new deep learning systems and artificial intelligence in general, in a way that is really, really beautiful and really outlines the ideas of what, in my opinion, artificial intelligence should be about. And let's finish with a quote. I will read it aloud. Just as there are odors that dogs can smell and we cannot, as well as sounds that dogs can hear and we cannot, so too there are wavelengths of light we cannot see and flavors we cannot taste. Why then, given our brains wire the way they are, those who remark perhaps there are thoughts we cannot think surprise you? Does it surprise you? Evolution so far may possibly have blocked us from being able to think in some direction. They could be unthinkable thoughts. And I hope that this talk proved you that using deep learning systems, we'll be able to build systems that would translate unthinkable to thinkable. Thank you very much. So, any questions? liked it.